More than 200 moons drift through our solar system, each one a world unto itself, carrying secrets that have taken billions of years to form. Some are coated in ice that hides vast oceans beneath, others blaze with volcanic fury, and a few spin through the darkness in ways that still puzzle the brightest minds on Earth. Tonight, as the world outside grows still, we turn our gaze to these silent companions of the planets, the moons that circle in quiet devotion through the endless night. Tonight, we explore the mysterious moons of our solar system, those distant worlds that orbit in shadow and starlight. They are places of wonder, where geysers erupt into the vacuum of space and frozen seas may harbor the conditions for life itself. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will carry you from moon to moon, through ice and fire and ancient stone. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever looked up at the moon and wondered what other moons might look like? What strange landscapes might await on worlds we have only glimpsed from afar? You are not alone. If these journeys through the solar system bring you peace, consider subscribing and sharing this channel with someone who might also enjoy falling asleep to the wonders of space. Take a slow breath in and let it go. Feel the weight of your body settle into wherever you are resting. Let your shoulders drop, your jaw soften, and allow the quiet hum of distant moons to begin. Let us begin. Our solar system is home to over 200 known moons. Across the vast expanse of our cosmic neighborhood, more than 200 moons drift in patient orbits around the 8 major planets and countless smaller bodies, each one a world unto itself, with its own story etched into rock, ice, and dust. Some are larger than entire planets, with atmospheres thick enough to hide their surfaces from view, while others are little more than tumbling boulders captured long ago by the gravity of their host. And together they form a silent congregation of worlds that most people will never see with their own eyes. Yet they are always there, circling in the darkness, shaping the rings of the giants, tugging at oceans of liquid beneath frozen shells, and carrying within them the chemical signatures of how our solar system came to be, reminders that even in emptiness there is company, and that the night sky holds far more neighbors than we often remember. We are not alone. The word moon comes from an ancient word meaning to measure time. Long before clocks ticked upon our walls or calendars marked the passage of days, ancient peoples looked to the sky and watched the moon grow from a sliver of pale light into a glowing disk, then shrink again into darkness. And in that steady rhythm, they found a way to measure the invisible flow of time, naming each cycle a month, a word that itself descends from the same root as moon. And so the moon became humanity's first timekeeper. A lantern in the night whose phases told farmers when to plant and harvest, guided travelers across unfamiliar lands, and marked the sacred festivals that bound communities together beneath its silver glow. And even now, though we carry precise machines in our pockets, the moon continues its ancient dance overhead, waxing and waning as it has for billions of years, indifferent to our technology, yet still casting its light upon anyone who cares to look upward and remember. Time circles on. Earth's moon is slowly drifting away from us at nearly 4 centimeters each year. With each passing year, the moon edges a little further from Earth, receding at roughly the same rate your fingernails grow, a motion so gentle that no human lifetime will notice the difference. Yet over hundreds of millions of years, this slow retreat will stretch the distance between us until the moon appears noticeably smaller in our sky, and the tides it commands will weaken. And the days themselves will lengthen as Earth's rotation gradually slows in response to the gravitational conversation between our two worlds, a dance that began when the moon was far closer and loomed enormous above ancient oceans, raising towering tides that crashed upon shores no creature had yet walked. And this quiet departure continues tonight while you rest, the moon creeping outward centimeter by centimeter, patient and unhurried. As though it knows that even the closest companions must one day allow a little more space between them. Distance grows softly. The moon was likely born from a catastrophic collision 4.5 billion years ago. In the violent youth of our solar system, when the planets were still finding their places and debris hurtled through space in every direction, a Mars-sized body struck the young Earth with unimaginable force, vaporizing rock and flinging molten material into orbit, where it swirled and cooled and slowly gathered into the sphere we now call the moon. And though this collision was catastrophic beyond anything humanity has ever witnessed, it may also have been essential for life on Earth. Tilting our planet just enough to give us seasons, steadying our rotation so that days and nights did not swing wildly in length, and pulling at our oceans in ways that may have helped the first living cells find nutrients along ancient coastlines. And so the moon that hangs peacefully in tonight's sky was forged in fire and chaos, a child of destruction that became a guardian of stability. From violence came calm. Our moon is the 5th largest in the entire solar system. Among all the moons that circle the planets of our solar system, Earth's companion ranks 5th in size, surpassed only by the great moons of the outer giants, Ganymede and Callisto of Jupiter, Titan of Saturn, and Io with its restless volcanoes. And yet when compared to the planet it orbits, our moon is remarkably large. So large, in fact, that some astronomers consider the Earth-Moon system to be a double planet rather than a simple world with a satellite. And this unusual size means the moon exerts a powerful influence on our tides, our axial tilt, and the very rhythm of life on Earth, a presence so significant that without it, the conditions for complex life might never have emerged. And so while moons far larger exist in the cold reaches beyond Mars, none holds quite the same relationship to its host as our own, a partner rather than a mere follower. Size alone does not tell the whole story. The moon always shows us the same face because it is tidally locked to Earth. Every time you gaze upon the moon, you see the same familiar pattern of dark plains and bright highlands, the same craters and the same shadowed valleys, because the moon rotates on its axis in exactly the same time it takes to orbit Earth, a phenomenon called tidal locking that arose over millions of years as Earth's gravity tugged at slight bulges in the lunar surface, until the moon's spin slowed and synchronized perfectly with its orbital period. And now it turns in a graceful pirouette that always keeps one hemisphere facing us, while the other remains forever hidden from ground-based eyes, a cosmic dance so precise that ancient observers believed the moon had no far side at all, only a single face gazing eternally earthward. And though we have since sent spacecraft around to photograph what lies beyond, the moon itself continues its locked rotation, a faithful partner who never looks away. One face, one gaze. The far side of the moon is not dark, but simply unseen from Earth. Often mistakenly called the dark side, the far hemisphere of the moon receives just as much sunlight as the face we know, experiencing its own sunrises and sunsets as it turns through the lunar day. Yet because the moon is tidally locked to Earth, this hemisphere always points away from our planet and was never glimpsed by human eyes until spacecraft ventured around in the 20th century. And when photographs finally arrived, they revealed a landscape strikingly different from the familiar near side. With fewer of the broad, dark plains called Maria and far more craters crowding its ancient surface, a terrain sculpted by billions of years of impacts with no volcanic floods to smooth them away. And this hidden hemisphere holds mysteries scientists are still working to understand. Questions about why the two sides differ so dramatically and what lies beneath the battered crust. And yet the sun still rises there, as it does everywhere, illuminating a world that is only dark to us. Hidden does not mean lightless. And from our own familiar moon, we now journey outward to the small, peculiar moons of Mars. Mars has two tiny moons named Phobos and Deimos, meaning fear and terror. Circling the red planet in swift, close orbits are two small moons whose names were drawn from the attendants of the Greek god of war, Phobos meaning fear and Deimos meaning terror, companions fitting for a world named after the Roman god Mars. And yet these moons are far from terrifying in appearance, resembling lumpy potatoes more than fearsome celestial bodies, their surfaces dark and pitted by countless impacts, their shapes too irregular to have formed from the slow accretion that built rounder worlds. And some scientists believe they may once have been asteroids wandering the inner solar system before Mars captured them in its gravitational embrace, while others suggest they could be remnants of a larger moon shattered by an ancient collision. And whatever their origin, they now circle Mars in eerie silence, Phobos drawing ever closer while Deimos drifts slowly outward, two companions locked in different fates around a world of rust-colored dust. Fear and terror keep quiet company. Phobos orbits so close to Mars that it will one day crash into the planet. Phobos races around Mars at such a low altitude that it completes 3 orbits for every Martian day, rising in the west and setting in the east as it overtakes the planet's own rotation. And with each circuit, it edges a tiny bit closer, drawn inward by tidal forces that steal energy from its motion. And in roughly 50 million years, give or take, Phobos will either slam into the Martian surface in a catastrophic impact or be torn apart by gravitational stresses as it crosses the invisible boundary where tides overpower the moon's own cohesion, creating a ring of debris around Mars that would slowly rain down upon the planet over millions of years more. And so this small, cratered moon is living on borrowed time in cosmic terms. A world destined to end not by drifting away like Earth's moon, but by falling ever closer until it can fall no further. The embrace will one day become too tight. Deimos is one of the smallest moons in the solar system. Measuring only about 12 kilometers across at its widest, Deimos is so small that an astronaut standing on its surface could walk around the entire world in a single day without breaking a sweat. Its gravity so feeble that a gentle jump would send you drifting upward for long minutes before you floated back down. And from that surface, Mars would dominate the sky like an enormous ochre disk. Close enough to reveal dust storms swirling across its plains, yet far enough to feel like a distant painting rather than a looming presence. And this tiny moon holds little in the way of drama, its craters softened by a layer of dust, its shape irregular but not as battered as its sibling Phobos, a quiet companion that orbits further out and drifts ever so slowly away from Mars as Phobos spirals inward, 2 moons on opposite trajectories, one shrinking toward its end and the other gently receding into the darkness of space. Even small worlds have their stories. Both Martian moons may be captured asteroids from the nearby belt. Just beyond the orbit of Mars lies the asteroid belt, a region strewn with rocky remnants left over from the solar system's formation. And some scientists believe that Phobos and Deimos were once wandering asteroids that strayed too close to Mars and were captured by its gravity, their dark, carbon-rich surfaces resembling the composition of certain asteroid types. Yet others argue that capture is dynamically difficult and propose instead that the moons formed from debris thrown into orbit after a massive impact on Mars itself, and the truth may lie somewhere in between or in a story we have not yet imagined. For the origins of these 2 small worlds remain one of the lingering puzzles of planetary science, a question that future missions may finally answer when spacecraft visit their surfaces and analyze the minerals beneath the dust. And until then, Phobos and Deimos continue their orbits, keeping their secrets tucked away like stones carried from a distant shore. Origin is not always written plainly. Phobos rises in the west and sets in the east on Mars. If you stood upon the rusty plains of Mars and watched the sky at dusk, you would witness something no earthly observer has ever seen: a moon rising from the western horizon rather than the east, arcing swiftly overhead and setting in the east just a few hours later. And this peculiar motion arises because Phobos orbits Mars faster than the planet rotates, completing its circuit in less than 8 hours, while the Martian day stretches to just over 24. And so from the surface, the little moon appears to move backward across the heavens, a cosmic reversal of everything we take for granted when we watch our own moon glide from east to west. And twice each Martian day, Phobos crosses the sky like a hurried traveler late for an appointment, too swift to linger, too close to appear as more than a small, oblong shape against the stars, a reminder that the rules of home do not always apply elsewhere. The westward rise is no illusion. Beyond Mars lies the giant Jupiter, a planet surrounded by a court of moons more varied than any other. Jupiter has over 90 known moons orbiting in a complex dance of gravity. The king of the planets holds court over a swirling family of moons so numerous that new members are still being discovered, with more than 90 confirmed satellites ranging from giant worlds larger than Mercury down to irregular boulders barely a kilometer across, and they move through space in a complex gravitational dance, some orbiting close to Jupiter in neat circular paths, others swinging far out on tilted, elongated trajectories that suggest they were captured long after the planet formed. And many of these outer moons travel in the opposite direction to Jupiter's spin, retrograde wanderers herded into loose groups that share similar orbits, hinting at a common origin in the breakup of larger bodies. And among this crowd, the 4 Galilean moons stand out like jewels in a crown, each one a world of wonders, while dozens of smaller companions flicker in and out of telescopic view. A reminder that even a single planet can host a miniature solar system of its own. Gravity gathers all who come near. Galileo discovered the 4 largest moons of Jupiter in 1610. In the winter of 1610, an Italian astronomer named Galileo Galilei turned his newly improved telescope toward Jupiter and noticed 4 faint points of light hovering near the bright disk of the planet, shifting their positions from night to night in a pattern that could only mean they were orbiting Jupiter rather than drifting randomly through the sky. And this simple observation shattered centuries of belief that everything in the heavens must revolve around Earth, providing powerful evidence for a cosmos in which other centers of motion existed. And the moons he spotted, now called Io, Europa, Ganymede, and Callisto, became known as the Galilean moons in his honor, 4 worlds that have since revealed themselves to be among the most fascinating destinations in the solar system, harboring volcanoes, hidden oceans, and ancient cratered plains. And yet it all began with a man peering through a small brass tube at lights no larger than pinpricks against the darkness. Curiosity opened the sky. Io is the most volcanically active body in the entire solar system. On the innermost of Jupiter's Galilean moons, volcanoes erupt with such relentless fury that the entire surface is reshaped within a matter of years, painting Io in shades of yellow, orange, red, and black, as sulfur compounds coat the landscape like layers of molten paint. And this turmoil arises not from heat left over from formation, but from the intense tidal forces exerted by Jupiter and its neighboring moons. Forces that flex and squeeze Io's interior until rock melts and magma surges upward through vents scattered across the globe. And the scale of this activity dwarfs anything on Earth, with hundreds of active volcanic centers detected, and some plumes of lava and gas rising high enough to be visible from orbit as faint fountains against the darkness of space. And yet, despite this violence, Io possesses a strange beauty, a world caught in a perpetual state of renewal, where no crater survives for long and every landscape tells a story measured in centuries rather than eons. Io burns so that it may live. And here, as you rest among these distant worlds, let your breathing settle into its own quiet rhythm. There is no need to follow every detail, no need to remember. Simply let the images drift through you like light through a window, and allow your body to soften wherever it may be holding tension. The volcanoes on Io are so powerful that they can launch material hundreds of kilometers into space. When a volcano erupts on Io, there is no thick atmosphere to hold the ejected material close to the surface, only the feeble grip of the moon's gravity and the vacuum of space. And so plumes of gas and molten particles can shoot upward at tremendous speeds, rising hundreds of kilometers above the surface before raining back down or escaping altogether into the region around Jupiter, where they contribute to a glowing donut of charged particles called the Io plasma torus that encircles the planet. And some of these eruptions have been photographed by passing spacecraft as faint umbrellas of debris silhouetted against the blackness, ghostly fountains that dwarf any geyser or volcanic plume on Earth. And the material that falls back reshapes the terrain continually, burying older features beneath fresh layers of sulfur and silicate. And all of this happens in relative silence. A furious dance of fire and ice taking place so far from human ears that it might as well be a dream. Power needs no audience. Io's surface is constantly being reshaped, erasing any impact craters within years. Most moons in the solar system wear their history on their faces, cratered and scarred by billions of years of impacts. But Io is different. Its surface so active that any crater formed by an incoming asteroid or comet is quickly buried beneath flows of lava and deposits of volcanic ash, erasing the evidence within years rather than the millions or billions required elsewhere. And this makes Io one of the youngest surfaces in the solar system, despite the moon itself being as old as Jupiter. A landscape reborn over and over again, like a chalkboard wiped clean each morning. And when spacecraft first flew past and returned images showing almost no impact craters, scientists realized they were looking at a world where geology outpaces cosmic bombardment, where the fires beneath the crust are more powerful than the violence raining down from above. And in this constant renewal, there is a kind of immortality, a surface that refuses to remember its wounds. The past is paved over. The intense radiation around Jupiter bombards Io with charged particles. Jupiter's magnetic field is the strongest of any planet, stretching far into space and trapping belts of high-energy particles that swirl around the planet in lethal bands. And Io orbits right through one of the most intense regions, bathed in radiation levels that would be fatal to any unprotected human within minutes. A relentless bombardment that strips atoms from Io's thin atmosphere and sends them spiraling along magnetic field lines to create glowing auroras in Jupiter's polar skies. And this radiation also interacts with the sulfur and oxygen escaping from Io's volcanoes, turning the space around the moon into a harsh environment where electronics fail quickly and biological molecules would be torn apart. And yet the volcanoes keep erupting, the surface keeps renewing, and Io continues its close orbit, as though indifferent to the invisible storm surrounding it, a testament to the resilience of geology against even the most hostile conditions imaginable. Life might not survive, but fire endures. Europa has a smooth, icy surface that may hide a vast ocean beneath. From a distance, Europa looks like a cracked egg, its surface a pale shell of water ice crisscrossed by reddish-brown streaks that hint at something moving below. And scientists now believe that beneath this frozen crust lies a global ocean of liquid water, kept warm by the same tidal forces that fuel Io's volcanoes, an ocean that may be more than 100 kilometers deep in places. And the smoothness of the surface suggests that the ice is not ancient, but continually refreshed. Broken apart by the flexing of the crust and refrozen into new patterns, and in some regions, rafts of ice appear to have drifted and rotated like pieces of a jigsaw puzzle, evidence that the shell floats upon something fluid, and this hidden sea has become one of the most tantalizing destinations in the search for life beyond Earth, a place where water, warmth, and chemistry may have mingled in darkness for billions of years, far from the sun, yet not far from possibility. Beneath the ice, something waits. The ocean beneath Europa could contain more water than all of Earth's oceans combined. Although Europa is smaller than our own moon, the ocean hidden beneath its icy shell may hold 2 to 3 times more water than every ocean on Earth put together, a staggering volume that would swallow all our seas and still have room to spare. And this abundance arises because Europa's ocean is thought to be very deep, perhaps extending more than 100 kilometers from the underside of the ice down to a rocky seafloor, whereas Earth's oceans average only a few kilometers in depth. And all of this water remains liquid not because of sunlight, but because of heat generated by the constant flexing of Europa's interior as Jupiter's gravity tugs at the moon in rhythm with its orbit. And if that ocean contains even a fraction of the chemistry needed for life, then Europa could harbor more living space than exists on the entire surface of our planet, hidden in perpetual darkness beneath a shell of ice. Volume is not everything, but it is a promising start. Scientists believe Europa is one of the most likely places to find life beyond Earth. In the search for places where life might have arisen independently of Earth, Europa consistently ranks among the top candidates, not because its surface is hospitable, for it is bitterly cold and bathed in radiation, but because the ocean beneath may possess all 3 ingredients that life as we know it requires: liquid water, a source of energy, and the right chemical building blocks. And on Earth, we have found thriving ecosystems around hydrothermal vents on the deep ocean floor. Places where no sunlight ever reaches, and yet bacteria and strange creatures flourish in the warm chemical soup spewing from cracks in the crust. And Europa's seafloor may host similar vents where heated water meets rock and releases nutrients into the darkness. And if even simple microbes exist there, drifting through that hidden ocean, it would change everything we know about our place in the universe, transforming life from a miracle of one world into a pattern repeated across the cosmos. The question is not if we should look, but when. From Europa's hidden waters, we turn to the largest moon in all the solar system. Ganymede is larger than the planet Mercury. Among all the moons circling every planet in the solar system, Ganymede stands supreme, its diameter stretching over 5,000 kilometers, making it larger than the innermost planet Mercury and roughly 3/4 the size of Mars. And if Ganymede orbited the Sun rather than Jupiter, it would easily qualify as a planet in its own right. A world of ice and rock with a thin atmosphere of oxygen and a complex surface, marked by both ancient dark regions pocked with craters and younger bright terrain grooved by tectonic forces that reshaped the crust long ago. And beneath this icy exterior lies a layered interior that may include a salty ocean sandwiched between shells of ice, a structure more intricate than most worlds possess. And standing on Ganymede, you would feel a gravity about 1/6 that of Earth. Light enough to jump several meters, yet heavy enough to keep you grounded beneath a sky dominated by the immense disk of Jupiter looming overhead. Size alone makes it a wonder. Ganymede is the only moon known to have its own magnetic field. Deep within Ganymede's interior, a core of liquid iron stirs and flows, generating a magnetic field that wraps around the moon like an invisible cocoon, a phenomenon unique among all the moons in the solar system, for even larger bodies like Titan and Callisto lack this internal dynamo, and this field is strong enough to carve out a small bubble within Jupiter's own immense magnetosphere, deflecting some of the charged particles that would otherwise bombard the surface. And the presence of a magnetic field tells scientists that Ganymede's core remains at least partially molten, a sign that heat still lingers within, perhaps enough to maintain that hidden ocean of liquid water between layers of ice. And around the moon's poles, this field funnels particles downward, creating faint auroras that glow in ultraviolet light, ribbons of luminescence that shift and shimmer as Ganymede rotates, a quiet light show witnessed only by passing spacecraft. Even moons can have their own magnetic souls. Beneath its icy crust, Ganymede may also harbor a salty ocean. Observations of Ganymede's auroras have revealed subtle oscillations that can best be explained by the presence of a conducting layer deep below the surface, and the most likely candidate is an ocean of salty water sandwiched between two thick layers of ice, the upper ice exposed to cold space and the lower ice pressed against the rocky mantle below. And this ocean may be over 100 kilometers deep, containing more water than all the lakes and rivers on Earth. A vast reservoir hidden in permanent darkness, where pressure and chemistry may create conditions unlike anything on our planet. And though the ice above and below would separate this ocean from both the surface and the rock, there remains a slim possibility that heat and nutrients could still find their way through, and future missions may one day probe this hidden sea, searching for signs that life might have taken hold in a place no sunlight ever reaches. Darkness does not preclude possibility. Callisto is one of the most heavily cratered objects in the solar system. The outermost of the 4 Galilean moons, Callisto orbits far enough from Jupiter that tidal heating has little effect on its interior, and without internal forces to resurface the crust, every impact crater that ever formed on Callisto remains visible today, creating a surface so densely packed that it resembles a battered shield recording billions of years of cosmic bombardment. And among these scars lies Valhalla, one of the largest impact structures in the solar system. A set of concentric rings spreading outward from a bright central region like ripples frozen in ice, a testament to a collision so powerful it sent shockwaves radiating across the entire hemisphere. And yet, despite this violence, Callisto appears serene from orbit, its ancient surface unchanging, its craters overlapping craters in a palimpsest of destruction and stillness, a world that simply accepted every blow without erasing the evidence, carrying its history openly for anyone who cares to look. The oldest stories are written in stone. Callisto's surface has remained largely unchanged for billions of years. While Io remakes itself every few years and Europa's ice shifts and cracks above its hidden ocean, Callisto has sat quietly at the edge of the Jovian system, geologically dead for so long that its surface is among the oldest in the solar system, a frozen record dating back nearly 4 billion years when the late heavy bombardment was drawing to a close and the inner planets were cooling from their violent births. And this antiquity makes Callisto a kind of time capsule, preserving conditions that have been erased elsewhere by tectonics, volcanism, or atmospheric weathering. And scientists value this stillness because it offers a window into the early solar system, a place where the original material of the Jovian region remains relatively untouched, waiting to be studied by future probes that may land on its dark, ice-rich terrain and dig into a past that other moons have long forgotten. Stillness can be its own kind of wealth. Jupiter's smaller moons orbit in wildly irregular patterns. Beyond the orderly paths of the Galilean moons lies a swarm of smaller satellites whose orbits tilt at steep angles, stretch into elongated ellipses, and in many cases carry the moons in the opposite direction to Jupiter's own rotation. And these irregular moons are thought to be the shattered remnants of comets or asteroids captured by Jupiter's gravity long ago, broken apart by collisions, and now drifting in loose families that share similar orbital characteristics. And some of these tiny worlds measure only a few kilometers across, dark and faint, discovered only in the past few decades as telescopes grew more powerful, and they move through regions of space where gravitational tugs from the sun and other bodies continually nudge their paths, making long-term prediction difficult. And in this chaotic outer realm, Jupiter plays the role of cosmic vacuum cleaner, sweeping up debris that might otherwise wander deeper into the solar system. A guardian that keeps the inner planets a little safer. Order and chaos both have their place. Some of Jupiter's outer moons orbit in the opposite direction to the planet's spin. Most moons in the solar system orbit in the same direction their planet rotates, a consequence of forming from the same spinning disk of material that gave birth to the planet itself. But many of Jupiter's outer moons break this rule, traveling in retrograde orbits that carry them backward against the planet's rotation, a telltale sign that they did not form alongside Jupiter, but were captured later. Wandering bodies whose paths brought them close enough to be snared by the giant's gravity and bent into new trajectories. And these retrograde moons tend to cluster in groups with similar orbits, suggesting that each group may have originated from a single larger body that fragmented under the stress of capture or collision, scattering pieces into a family of shared motion. And as they circle in their contrary fashion, they occasionally cross paths, with moons traveling the other way, leading to further collisions that continue to shape the population. Rebellion is sometimes evidence of origin. And now we leave Jupiter behind, drifting further still to the ringed beauty of Saturn. Saturn has over 140 known moons, more than any other planet. Surrounded by its iconic rings, Saturn also hosts the largest family of moons in the solar system, with more than 140 confirmed satellites ranging from the giant Titan, larger than Mercury, down to tiny moonlets embedded within the rings themselves, some no bigger than a city block. And this abundance continues to grow as astronomers discover ever smaller objects circling the planet, pushing the count higher with each passing year. And the moons of Saturn display an astonishing variety, from Titan's thick orange atmosphere to the icy geysers of Enceladus, from the heavily cratered face of Mimas to the two-toned mystery of Iapetus. And together they form a system within a system, a miniature solar system orbiting the ringed giant, each moon influencing the others through gravity, shaping the rings, exchanging material, and creating a dynamic environment that scientists are still working to fully understand. Saturn's court is the grandest of all. Titan is larger than Mercury and has a thick, hazy atmosphere. Saturn's largest moon is a world unlike any other in the solar system, wrapped in an orange haze so thick that its surface remained hidden until spacecraft flew close enough to peer through with radar and infrared instruments. And this atmosphere is made mostly of nitrogen, with a smaller fraction of methane and other organic molecules, extending higher above the surface than Earth's own atmosphere relative to the size of the body, creating a pressure at ground level about 1.5 times that of our planet's sea level. And beneath the smog lies a landscape of dunes, mountains, and liquid lakes, a cold alien world where temperatures hover around -180 degrees Celsius, and the chemistry of life's building blocks plays out in slow motion under a dim, distant sun. And if you could stand on Titan's surface, you would feel the thick air pressing gently against you and see an orange twilight stretching to the horizon. It is a world of familiar processes in unfamiliar guise. Titan is the only moon in the solar system with a dense atmosphere. While many moons possess thin wisps of gas around them, only Titan has an atmosphere substantial enough to obscure the surface from view and to support weather patterns that rival those on Earth, with clouds forming, rain falling, and winds shaping the terrain below. And this unique atmosphere likely persists because Titan is cold enough for nitrogen to remain bound by gravity rather than escaping into space, and because the chemistry of sunlight breaking down methane releases products that rain back down and are recycled through geological processes. a cycle that keeps the atmosphere replenished over geological time. And the presence of such a substantial gaseous envelope makes Titan a natural laboratory for studying atmospheric chemistry. A place where the building blocks of life may be assembling in forms we do not yet recognize, waiting patiently in the deep chill for conditions that may never warm enough to spark biology as we know it. An atmosphere can be a world unto itself. Rain falls on Titan, though it is made of liquid methane rather than water. On Titan, the hydrological cycle familiar from Earth plays out with a different cast of molecules, for methane takes the place of water, evaporating from lakes and seas into the thick atmosphere, condensing into clouds, and falling back to the surface as rain that carves channels into the icy terrain. And this methane rain is thought to be gentle, drifting down through the dense air in large, slow drops that would feel more like a soft mist than a proper downpour. And seasonal storms have been observed by spacecraft, great cloud systems moving across the moon's disk and releasing their cargo onto the landscape below. And the cycle continues as the methane drains through rivers into seas near the poles, only to evaporate and rise again, a patient rhythm repeated over millions of years beneath a sun so distant it appears as little more than a bright point in the hazy sky. Rain can be made of many things. Rivers and lakes of hydrocarbons carve the surface of Titan. Spacecraft equipped with radar have revealed a surface etched by winding channels that drain into broad lakes and seas, features that would look familiar to anyone who has seen an aerial photograph of Earth's river deltas, except that the liquid flowing through these channels is not water, but a mixture of methane and ethane, hydrocarbons that remain liquid in the frigid temperatures of Titan's surface, and some of these lakes are larger than the Great Lakes of North America. Vast reservoirs reflecting the faint glow of a hazy sky, while others are small ponds tucked into valleys and craters, and the shorelines show evidence of changing levels, hints that Titan experiences seasons during its roughly 29-year orbit around Saturn, with some regions drying out and others filling as the climate shifts. And beneath this alien hydrology lies a crust of water ice hard as rock, a landscape shaped by processes both strange and wonderfully familiar. Erosion speaks a universal language. The Huygens probe landed on Titan in 2005 and sent back the first images from its surface. After a 7-year journey strapped to the side of the Cassini spacecraft, a small probe named Huygens separated and began its descent through Titan's thick atmosphere, drifting downward on parachutes, while instruments measured temperature, pressure, and chemical composition. And for more than 2 hours, it fell through the haze, sending back data and images that revealed a world of orange skies and eroded hills. Until at last, it touched down on a surface that gave way slightly beneath its weight like wet sand or frozen mud. And the photographs it returned showed rounded pebbles of water ice scattered across a dark plain, evidence of past flooding or erosion. And for another 70 minutes, the probe continued to transmit, painting a picture of an alien landscape both eerie and oddly Earth-like, a place where clouds drifted overhead and frozen rivers had once flowed. And then the signal faded. Huygens falling silent on a world more than 1 billion kilometers from home. It was a brief visit, but what it showed us will last forever. Enceladus shoots geysers of ice and water vapor into space. Near the south pole of this small icy moon, plumes of water vapor and ice crystals erupt continuously from long fractures in the surface known as tiger stripes, jetting outward at hundreds of meters per second, and forming a faint spray that extends far above the moon before some particles fall back, while others escape into orbit around Saturn. And the Cassini spacecraft flew through these plumes multiple times, tasting the material within and detecting not only water, but also salts, silica, and organic molecules, ingredients that point to a warm, chemically rich source below. And the very existence of these geysers tells us that liquid water persists beneath the frozen shell, heated by tidal forces, even though Enceladus is only about 500 kilometers across, a world so small it would fit comfortably within the borders of England, and yet it roars into the vacuum with continuous fountains of mist. A spectacle of activity on a moon that by all rights should be frozen solid. Small things can make a big noise. The geysers of Enceladus feed material directly into Saturn's rings. Much of the ice and vapor ejected by Enceladus escapes the moon's feeble gravity and drifts into orbit around Saturn, spreading out into a faint torus known as the E-ring, one of the outermost rings of the planet. And unlike the bright main rings made of ancient debris, the E-ring is constantly being replenished by fresh material spraying from Enceladus, giving it a diffuse, ghostly appearance that stretches across a vast region of space. And particles from this ring eventually settle onto other moons in the area, coating their surfaces with a fine layer of ice dust from Enceladus, linking these worlds in a web of shared material. And so this tiny moon acts as a cosmic sprinkler, continuously seeding the Saturnian system with water ice that carries the chemical signatures of its hidden ocean, evidence that what lies beneath one world can reach far beyond its own borders. One moon's interior becomes another moon's surface. Beneath the frozen shell of Enceladus lies a global ocean. Analysis of how Enceladus wobbles as it orbits Saturn revealed that the icy shell is not firmly attached to the rocky interior, but floats on a layer of liquid that allows it to librate more than a solid body would. And further study showed that this liquid layer extends beneath the entire moon rather than being confined to the South Polar region where the geysers emerge, a global ocean trapped between ice and rock. Perhaps only a few tens of kilometers deep, but enough to hold as much water as some of Earth's smaller seas. And this ocean is warmed from below by hydrothermal activity, heat generated by tidal friction flexing the rocky core and releasing energy into the water above. And the plumes we see are windows into this hidden realm, samples drawn up from the depths and delivered freely into space for spacecraft to analyze. A gift that makes Enceladus one of the most accessible ocean worlds in the solar system. The shell conceals, but the geysers reveal. Organic molecules have been detected in the plumes of Enceladus. When Cassini flew through the icy spray erupting from Enceladus, its instruments detected not only water and salts, but also complex organic molecules, carbon-bearing compounds that form the backbone of life as we know it. And while the presence of organics does not prove that life exists beneath the ice, it does confirm that the ocean contains the kinds of chemistry from which living systems could potentially arise. And some of these molecules are large and complex, suggesting chemical reactions taking place in the warm, mineral-rich environment near hydrothermal vents on the ocean floor, conditions that mirror those believed to have nurtured the earliest life on Earth billions of years ago. And this discovery has elevated Enceladus to the top tier of targets in the search for extraterrestrial life. A small icy moon that may harbor within its hidden sea the answer to one of humanity's oldest questions. If life can begin anywhere, why not there? Mimas has a giant crater that makes it look like the Death Star from Star Wars. One of Saturn's smaller moons bears a scar so prominent that when the first detailed photographs arrived on Earth, observers immediately noticed its resemblance to the fictional space station from the Star Wars films. A coincidence of timing, since the film was released before the moon was photographed at close range. And this crater, named Herschel after the astronomer who discovered Mimas, stretches nearly 1/3 the diameter of the entire moon. A vast bowl with walls rising several kilometers above the floor and a central peak jutting upward like the tip of a frozen wave. And the impact that created Herschel must have come within a whisker of shattering Mimas entirely, sending cracks radiating across the opposite hemisphere and leaving a permanent reminder of the violence that shaped the early solar system. And today Mimas orbits silently, its giant eyes staring forever into space. A small world marked by one enormous wound that it wears without complaint. Survival sometimes leaves scars. The crater on Mimas is so large that the impact nearly shattered the moon. Scientists estimate that the object which struck Mimas to create Herschel was traveling at tremendous speed when it collided with the icy moon, releasing enough energy to send shockwaves reverberating through the entire body and fracturing the hemisphere on the opposite side. And had the impactor been only slightly larger or moving a bit faster, Mimas would have broken apart into a cloud of debris, perhaps eventually forming a new ring around Saturn or coalescing into a swarm of smaller fragments. And the fact that Mimas survived at all is a testament to the fine balance between destruction and persistence that governs the fate of small bodies in the solar system. A coin flip outcome frozen in ice for billions of years, and now the moon continues its quiet orbit, carrying within it the memory of an impact that came within a razor's edge of ending its existence. A reminder that the line between a moon and a ring can be thinner than we imagine. Near misses shape the cosmos too. Let these distant worlds settle gently into the background of your thoughts. If your mind has wandered, that is perfectly fine. Allow yourself to sink a little deeper now, feeling the soft pull of rest. Your breath continues, steady and slow, and there is nowhere else you need to be. Iapetus has one side as dark as coal, and another as bright as snow. Of all Saturn's moons, Iapetus presents the most striking visual mystery. One hemisphere coated in material so dark, it reflects barely a few % of the light that falls upon it, while the other gleams with ice as bright as fresh snow. And this two-toned appearance puzzled astronomers for centuries, until spacecraft revealed that the dark material originates from nearby moons whose dusty debris drifts inward and settles on Iapetus's leading hemisphere as it plows through the tenuous cloud. And once this dark layer begins to accumulate, it absorbs more sunlight and warms slightly, causing underlying ice to sublimate and migrate to the cooler, bright hemisphere, a runaway process that exaggerates the contrast over time until the moon resembles a cosmic yin-yang symbol, half shadow and half shine. And this strange partition makes Iapetus one of the most photogenic worlds in the solar system, a place where light and dark meet along a border visible from orbit. Contrast can define a world. A towering ridge runs around the equator of Iapetus. Stretching for more than 1,000 kilometers along the equator of Iapetus is a chain of mountains so tall and so precisely aligned that it looks almost artificial, a spine of peaks rising up to 20 kilometers above the surrounding terrain, 3 times the height of Mount Everest, cutting the moon's midsection like a seam on a walnut, and no other body in the solar system possesses anything quite like it, and scientists remain uncertain how this ridge formed. Whether it is the remnant of a former ring that collapsed onto the surface long ago, a bulge frozen in place when the moon spun faster and then slowed, or the product of tectonic compression that pushed material upward along a fault line, and each hypothesis has strengths and weaknesses, leaving the ridge as one of the great unsolved puzzles of planetary geology, a feature so dramatic it seems to demand an equally dramatic explanation that we have yet to find. Some mysteries circle the world. Hyperion has an irregular shape and tumbles chaotically through space. Among Saturn's many moons, Hyperion stands out for its strange, sponge-like appearance and its unpredictable rotation. For rather than spinning on a fixed axis like most bodies in the solar system, Hyperion tumbles end over end in a chaotic pattern that makes it impossible to predict which face will point toward the sun from one orbit to the next. And this erratic motion arises from its irregular shape and its gravitational interactions with nearby Titan. Influences that prevent it from settling into a stable spin state, and the surface is pocked with deep craters whose floors are coated with dark material, giving the moon a texture reminiscent of a deep-sea sponge or petrified coral, a honeycomb world drifting through space with no sense of up or down, and if you stood upon its surface, you would feel gravity so feeble that you could leap into orbit with a running start, untethered and tumbling just like the moon itself. Stability is not always the rule. Phoebe is thought to be a captured object from the outer solar system. Orbiting far from Saturn on a tilted, retrograde path, Phoebe is unlike the icy moons that formed alongside the planet, its composition suggesting instead that it originated in the distant Kuiper belt and was captured by Saturn's gravity when it strayed too close during the chaotic rearrangements of the early solar system. And its dark surface is peppered with craters that have excavated brighter ice from below, revealing layers that record a history stretching back billions of years to a time before it wandered inward. And studies of Phoebe's density and reflectivity indicate a mixture of ice, rock, and carbon-rich materials similar to comets, making it a visitor from the cold frontier, now trapped in endless orbit around a giant world it was never meant to serve. And the dust, knocked off Phoebe by impacts, drifts inward and coats the leading hemisphere of Iapetus, linking these two moons in an asymmetric partnership. Origins are not always local. Dione shows evidence of past geological activity beneath its icy surface. Dione's surface is a map of two different eras, one hemisphere heavily cratered and ancient, while the other displays bright ice cliffs and smooth plains that suggest the moon was resurfaced by internal activity at some point in its history, perhaps by cryovolcanism that pushed warm, slushy ice up through fractures in the crust, and spacecraft have detected a faint wisp of atmosphere around Dione, mostly oxygen released when charged particles from Saturn's magnetosphere strike the icy surface and liberate molecules locked in the frozen lattice. And there are hints that an ocean may lurk beneath the ice here as well, though evidence remains inconclusive. And if warm water once flowed beneath Dione's crust, it has left its mark in the form of bright streaks and grooves that crisscross the trailing hemisphere, features that speak of a world not entirely frozen in place. A world that remembers motion even if motion has long since ceased. The past can leave bright traces. Tethys has a canyon that stretches nearly 3/4 of the way around the moon. Carved into the icy surface of Tethys is a rift valley named Ithaca Chasma, a scar so long and so deep that it extends for over 2,000 kilometers, wrapping nearly 3/4 of the way around the moon, with walls rising several kilometers on either side and a floor that drops far below the surrounding terrain. And this immense canyon is thought to have formed when the interior of Tethys froze and expanded, cracking the crust like an overfilled ice cube. Or perhaps in response to the shock from the massive impact that created the crater Odysseus on the opposite hemisphere, a blow that may have sent fractures radiating through the entire body. And today Ithaca Chasma remains as a testament to forces that once gripped the moon in a moment of stress, a wound that spans continents on a world only 1,000 kilometers wide, silent and still beneath the distant light of the sun. Some fractures are too large to hide. Rhea may have a faint ring system of its own. Saturn's second largest moon has offered hints of something unusual, for instruments aboard Cassini detected strange patterns in the flow of charged particles around Rhea, patterns that could be explained by a tenuous ring of debris orbiting the moon. And if confirmed, this would make Rhea the first moon known to possess its own ring, a thin veil of dust and ice circling a world that itself circles a planet famously adorned with rings, a nesting doll arrangement of orbital elegance. Yet direct images have not conclusively detected this ring, leaving its existence an open question that future missions may resolve. And whether the particles are truly there or the signatures arise from some other cause, the possibility alone reminds us that moons are not passive objects, but dynamic worlds capable of holding their own entourages, small kingdoms within larger kingdoms, and the solar system may hold many such surprises waiting to be found. Rings within rings, is a pattern nature loves. From the icy kingdoms of Saturn, we now venture to the tilted giant Uranus and its strange moons. Uranus has 27 known moons, all named after characters from literature. Unlike the moons of other planets, which draw their names from Greek and Roman mythology, the moons of Uranus are named for characters from the works of William Shakespeare and Alexander Pope, a tradition begun by the son of the astronomer who discovered the planet and continued to this day. And so orbiting this tilted ice giant are Oberon and Titania from A Midsummer Night's Dream, Ariel and Miranda from The Tempest, and a host of others drawn from plays and poems. Fairies and spirits given new life as distant worlds of rock and ice, and these 27 known moons range from small irregular boulders only a few tens of kilometers across to substantial satellites with complex surfaces and hints of past geological activity, and all of them orbit in the same tilted plane as Uranus itself, circling a planet that rolls through space on its side as though knocked over by some ancient collision. And in this eccentric realm, literature and astronomy meet beneath a faint, frigid sun. Names can give cold worlds a touch of poetry. Miranda has one of the most chaotic surfaces in the solar system. When Voyager 2 flew past Uranus in 1986, it returned images of Miranda that left scientists astonished. For this small moon, barely 500 kilometers across, displayed a surface unlike any other, a patchwork of ancient cratered plains abutting bizarre regions of ridges and grooves known as coronae, as though the moon had been assembled from mismatched pieces or torn apart and hastily reassembled. And one leading theory proposes that Miranda was indeed shattered by a massive impact and then slowly coalesced back together, its interior still differentiating as dense material sank and lighter ice rose, leaving the surface a geological jigsaw of competing terrains, while another theory suggests that internal heating drove tectonic forces that reshaped parts of the crust while leaving others untouched, and whichever explanation is correct. Miranda remains one of the most visually striking moons ever photographed, a tiny world that wore its turbulent history openly. Chaos can be beautiful. Cliffs on Miranda are the tallest in the solar system. Rising from Miranda's jumbled terrain is a sheer cliff named Verona Rupes, a wall of ice and rock that plunges an estimated 20 kilometers from rim to floor, more than 10 times the depth of the Grand Canyon, and tall enough that if you dropped a stone from the top, it would take nearly 10 minutes to reach the bottom in Miranda's weak gravity, drifting downward slowly rather than plummeting. And this immense escarpment is thought to have formed through a combination of faulting and collapse. Perhaps when sections of the crust shifted during the moon's turbulent past, leaving behind a precipice so vast it would dwarf any cliff on Earth. And though no human has ever stood at its edge, the images returned by Voyager 2 show a darkness at the base where shadow falls and a brightness at the top where sunlight grazes the rim, a landscape of extremes on a world where extremes seem to be the norm. Height is relative, but this is extraordinary. Ariel shows signs of past cryovolcanism, where icy slush once flowed like lava. Among the moons of Uranus, Ariel displays the youngest and brightest surface, marked by valleys and smooth plains that suggest material once welled up from below and spread across the terrain before freezing solid, a process scientists call cryovolcanism because the erupting substance is not molten rock, but rather a slurry of water ice, ammonia, and other volatiles that behave like lava in the frigid temperatures of the outer solar system. And the valleys on Ariel are deep and often filled with what appears to be frozen flow material, evidence that heat once reached the interior despite the immense distance from the sun, perhaps through tidal forces that have since faded as orbital resonances shifted over time. And today Ariel is quiet. Its cryovolcanic era ended, but the landforms it left behind are a record of a warmer past when this small moon had an active heart. And that record remains written in ice for anyone patient enough to read it. Ice can flow when given reason. Umbriel is one of the darkest moons orbiting Uranus. Compared to its brighter siblings, Umbriel reflects so little light that it appears almost coal-like in photographs, its surface coated with a layer of dark material whose origin remains uncertain, perhaps carbonaceous compounds deposited by impacts or produced by radiation interacting with surface ice over billions of years. And this darkness gives Umbriel a somber appearance, a moon that seems to absorb more than it gives back. And yet within one large crater, a bright ring of material stands out against the gloom, a feature nicknamed Wonder, possibly the exposed ice of an ancient impact now contrasting starkly with the surrounding terrain. And aside from this single bright spot, the surface is uniformly old and cratered, showing no signs of the geological renewal seen on Ariel or the chaotic reshaping of Miranda, a world that settled into stillness long ago and has remained there ever since, darkening with each passing eon. Stillness wears shadow well. Titania is the largest moon of Uranus and has vast canyons. Titania is the queen among Uranus's moons, fittingly named for the fairy queen in Shakespeare's play, and its surface reveals a complex history etched in deep fault valleys and impact craters, some of the canyons stretching for hundreds of kilometers across the icy terrain, evidence of a period when the moon's interior expanded as water froze and cracked the crust, and there are hints that cryovolcanic flows once filled some of these valleys, smoothing their floors with fresh ice before the interior cooled and all activity ceased. And Titania stands as the largest of the Uranian system, about half the size of Earth's moon, yet receiving so little sunlight at this distance that surface temperatures plunge to around -200 degrees Celsius, a cold that makes ice as hard as rock and preserves features for billions of years. And in that frigid preservation, the story of Titania's active youth remains legible to those who can read the language of fractures and flows. Royalty does not always mean warmth. Oberon is heavily cratered and has a mysterious dark material on its floor. The outermost of Uranus's large moons, Oberon presents a surface battered by countless impacts, its terrain so ancient and cratered that little geological activity seems to have occurred since the early bombardment era billions of years ago. And on the floors of some of its largest craters lies a dark material whose nature remains unexplained, possibly the ooze of cryovolcanic eruptions that brought carbon-rich compounds to the surface long ago. Or perhaps the residue of impactors that delivered organics from the outer solar system, and one mountain near the limb of the moon rises more than 6 kilometers above the surrounding terrain, a lonely peak on a world far from the sun's warmth, and Oberon carries its scars openly, a record of violence that has not been erased by any subsequent activity. And in this stillness, there is a kind of purity, a world that stopped changing so long ago that time itself seems frozen into its icy crust. Antiquity wears shadow gently. Farther still lies Neptune, the last giant, with moons that whisper of stolen worlds. Triton is Neptune's largest moon and orbits in the opposite direction to the planet's spin. Among all the large moons in the solar system, Triton stands alone in its defiance, circling Neptune in a retrograde orbit that carries it backward against the planet's rotation, a trajectory that cannot have arisen if Triton formed alongside Neptune from the same disk of material. And this backward motion is the strongest evidence that Triton was once a dwarf planet wandering the Kuiper belt until Neptune's gravity captured it long ago. Bending its path into a new orbit and condemning whatever original moons the planet may have had to destruction or ejection as the newcomer disrupted the system. And today Triton is the only large moon Neptune retains, a stolen world now trapped in a slow inward spiral that will one day bring it close enough to be torn apart by tidal forces. But for now, it remains a captive jewel, reflecting sunlight across frozen plains and erupting geysers of nitrogen into the thin atmosphere. Captives can still be wondrous. Triton was likely captured from the Kuiper Belt long ago. Beyond the orbit of Neptune lies the Kuiper Belt, a vast ring of icy bodies left over from the solar system's formation. And Triton's composition and orbit suggest it once roamed freely among these distant wanderers before an encounter with Neptune redirected its path, perhaps through a collision with an original Neptunian moon, or by plowing through a disk of debris that slowed it enough to be captured. And the energy released during this process would have heated Triton's interior for millions of years, melting ice and potentially creating conditions for a subsurface ocean that may persist to this day. And Triton's density and surface chemistry resemble those of Pluto, another Kuiper Belt object, reinforcing the idea that these two worlds are siblings by origin if not by fate, one captured into servitude around a giant planet, while the other continues its lonely circuit in the outer darkness. Kinship can span great distances. Geysers on Triton shoot nitrogen gas and dark dust into its thin atmosphere. When Voyager 2 flew past Triton in 1989, it photographed dark streaks on the icy surface and traced them back to plumes of nitrogen gas erupting from beneath the frozen crust. Geysers that rise several kilometers into the thin atmosphere before the wind carries their dusty payloads downwind across the terrain, leaving dark smudges that mark the direction of the prevailing breeze. And these eruptions are thought to occur when sunlight penetrates the translucent nitrogen ice and warms the material beneath, building pressure until it bursts through the surface in a sudden release. A solar-powered fountain on a world where the sun appears little brighter than a distant star, and each geyser paints a new streak on the landscape, slowly reshaping the surface over millennia. And so even at the frigid edge of the solar system, where temperatures hover around -235 degrees Celsius, activity persists. Cold does not mean dead. Triton's surface is a frozen landscape of nitrogen ice and cantaloupe terrain. Much of Triton's surface is blanketed by nitrogen and methane ices that shift with the seasons, sublimating in the weak sunlight and refreezing in shadow, and large regions display a peculiar texture of rounded depressions resembling the skin of a cantaloupe melon, terrain unique in the solar system and thought to result from the slow churning of surface material driven by temperature differences or the collapse of ancient ice features, and elsewhere the landscape is smoother, crisscrossed by ridges and fractures that hint at past tectonic activity, and there are few impact craters visible, evidence that the surface is relatively young and has been reshaped by geological processes within the last few 100 million years. And standing on Triton, one would see a pale, eerie world bathed in the faint light of a sun so distant it provides little warmth, yet still powerful enough to drive subtle changes across this frozen expanse. Beauty can be found even in the furthest cold. Triton is slowly spiraling inward and will one day be torn apart by Neptune. Because Triton orbits in the opposite direction to Neptune's rotation, tidal interactions between the Moon and the planet drain energy from Triton's orbit, causing it to inch closer with each circuit, a process that has been ongoing since the capture event billions of years ago and will continue for billions more until the Moon crosses the Roche limit, the invisible boundary where tidal forces exceed the gravitational cohesion holding Triton together. And at that point, the Moon will be torn apart, its fragments spreading into a ring of debris around Neptune that may rival or surpass the rings of Saturn in grandeur before eventually raining down onto the planet below. And so Triton's fate is sealed, a stolen world doomed to destruction by the very forces that captured it. But that end lies perhaps 3.5 billion years in the future, time enough for countless sunrises and geysers and seasons of ice. Endings can be patient. Neptune has 13 other moons, most of them small and irregular. Aside from Triton, Neptune hosts more than a dozen smaller satellites, most of them dark, irregularly shaped bodies measuring only a few tens of kilometers across, tumbling through space on orbits that tilt at odd angles or swing far from the planet in elongated ellipses. And these moons are thought to be remnants of a larger population that was disrupted when Triton arrived and scattered the original system. Survivors that now circle in the gravitational chaos left behind by that ancient capture event, and some orbits so far from Neptune that they take years to complete a single circuit, faint and distant, barely visible even to the most powerful telescopes. And yet each one holds clues to the early history of the Neptunian system, fragments of a story that was rewritten when Triton became the dominant moon and reshaped everything around it. The small remember what the large forgot. Nereid has one of the most eccentric orbits of any moon in the solar system. Nereid swings around Neptune on a path so elongated that its distance from the planet varies by a factor of 7 over the course of its roughly 360-day orbit, plunging close to Neptune at periapsis and then retreating far out into space at apopsis. And this extreme eccentricity is almost certainly a scar left by the capture of Triton. For Nereid may once have orbited in a more circular path before gravitational perturbations from the newcomer kicked it into its current stretched trajectory, and today Nereid tumbles through space as a dark, irregularly shaped body about 340 kilometers across, catching only brief glimpses from passing spacecraft, its rotation and composition still poorly understood, and in its wild orbit there is a story of disruption. Of a moon that survived the arrival of a rival but was never the same afterward. Orbits remember upheaval. And now, beyond the realm of the giants, we find the dwarf planets and their tiny companions. Pluto has 5 known moons, the largest of which is Charon. Out in the cold reaches of the Kuiper Belt, Pluto drifts through space accompanied by a retinue of 5 moons, the largest of which, Charon, is so substantial that the two bodies orbit a common center of gravity that lies outside Pluto itself, making them more of a double dwarf planet than a simple primary and satellite, and the 4 smaller moons, Nix, Hydra, Kerberos, and Styx, tumble chaotically in the outer regions of this system. Their rotations so unpredictable that no single face ever points steadily at Pluto, and this little family of worlds orbits the Sun together in a slow dance that takes nearly 250 years to complete. So far from the light that noon on Pluto is no brighter than twilight on Earth, and yet even here there is wonder, ice mountains and nitrogen glaciers and skies tinted with the faint glow of a sun that appears as little more than a bright star. Distance does not diminish complexity. Charon is so large compared to Pluto that they orbit each other like a double system. While most moons are dwarfed by the worlds they circle, Charon is more than half Pluto's diameter and roughly 1/8 its mass, proportions so close that the two bodies revolve around a point in space that lies between them rather than inside Pluto, a barycenter that wobbles back and forth as the pair completes their mutual orbit. And from this geometry arises the notion of a binary system, 2 worlds locked together by gravity, neither fully dominant, each influencing the other's tides and rotation. And the space between them stretches roughly 20,000 kilometers, close enough that Pluto looms large in Charon's sky, and Charon hangs huge above Pluto's horizon, never setting for observers on the facing hemispheres, a permanent fixture in the sky as unchanging as the frozen landscape below. And in this partnership, there is a kind of balance, 2 small worlds finding stability together in the outer darkness. Some companions are nearly equals. Pluto and Charon are tidally locked, always showing the same face to one another. Over billions of years, The gravitational tugs between Pluto and Charon have slowed their rotations until both bodies now spin in perfect synchrony with their orbital period, completing one rotation for every orbit so that the same hemisphere of each world forever faces its partner. And this double tidal lock is a rare arrangement. For while many moons are locked to their planets, it is unusual for the planet itself to be locked in return. And the result is a cosmic waltz where neither partner ever looks away, Pluto's near side always gazing at Charon's near side, day after day, year after year, for eons stretching back to the distant past and forward into an indefinite future. And if you stood on the wrong hemisphere, you would never see the other world at all, only the stars wheeling overhead in a cold sky, unaware of the companion hiding behind the horizon. Mutual gaze, mutual stillness. Charon has a reddish polar cap made from material escaping Pluto's atmosphere. When New Horizons flew past the Pluto system in 2015, it captured images of Charon that revealed a dark reddish stain around the moon's north pole, a feature scientists named Mordor Macula after the shadowy realm in Tolkien's fiction. And this coloration arises from gases escaping Pluto's thin atmosphere, drifting across the space between the two worlds and settling onto Charon's frigid polar region, where extreme cold traps them in place and solar radiation transforms simple molecules like methane into complex organic compounds called tholins, ruddy substances that tint the ice with hues of red and brown. And this process continues today, Pluto gradually painting its companion with the exhaust of its own atmosphere, a slow transfer of material that links the two bodies in yet another way. And in millions of years, the polar cap may grow darker still. A reminder that even at the edge of the solar system, worlds can share more than gravity. Atmosphere can travel. As we drift past these distant companions, let your thoughts grow soft and weightless. Breathe gently, feeling the rise and fall of your chest like the slow orbit of a moon around its planet. There is nothing you need to do, simply rest. Nix and Hydra are tiny moons of Pluto that tumble chaotically in space. Beyond Charon orbit four much smaller moons, and among them Nix and Hydra stand out as the brightest and first discovered, irregular chunks of ice measuring only a few tens of kilometers across. And unlike most moons that spin steadily on a single axis, Nix and Hydra tumble chaotically, their orientations shifting unpredictably as the combined gravitational pulls of Pluto and Charon push and pull them in complex ways. And this chaotic rotation means that any observer standing on the surface would see the stars wheel overhead in patterns that never repeat, a sky in constant flux, and the surfaces themselves are surprisingly bright, reflecting light with an intensity that suggests fresh ice rather than the dark tholins coating Charon's pole. And in their small, tumbling existence, these moons carry clues about the collision that may have created the Pluto-Charon system long ago. Debris flung outward and captured into orbits that have never found true rest. Chaos can be a kind of freedom. Kerberos and Styx are so small that they were not discovered until 2011 and 2012. Even after decades of careful observation, Pluto's smallest moons remained hidden until the Hubble Space Telescope detected them in the years leading up to the New Horizons flyby, faint specks of light that required multiple exposures to distinguish from the background noise. And these moons, named Kerberos and Styx after figures from Greek mythology, measure only a handful of kilometers across, irregular in shape and tumbling like their larger siblings Nix and Hydra. And their late discovery highlights just how much remains unseen even in our own solar system. Small worlds hiding in plain sight until technology and patience reveal them. And the data returned by New Horizons showed Kerberos to be darker than expected, perhaps hinting at a different composition or history from the brighter moons nearby. And together these four small satellites complete a family bound to Pluto by gravity and possibly by birth. some companions are shy. Eris, a dwarf planet beyond Pluto, has a moon named Dysnomia. Far beyond Pluto's orbit lies Eris, a dwarf planet so distant that it takes more than 500 years to circle the Sun. And accompanying this remote world is a small moon named Dysnomia, the daughter of the Greek goddess of strife in mythology, a fitting companion for a world whose discovery helped spark the debate that led to Pluto's reclassification as a dwarf planet. And Dysnomia's orbit has allowed astronomers to measure the mass of Eris with surprising precision, confirming that it is slightly more massive than Pluto despite being a bit smaller in diameter, a denser, more compact world made perhaps of more rock and less ice. And together Eris and Dysnomia drift through the outer darkness in a slow waltz that few will ever glimpse directly, yet their existence reminds us that the solar system extends far beyond the familiar planets, into realms where sunlight is a distant memory. Even the Edge has companions. Haumea is a fast-spinning dwarf planet with 2 tiny moons. Haumea spins so rapidly that its shape has been stretched into an elongated ellipsoid, completing a rotation in under 4 hours and bulging noticeably at the equator. And orbiting this unusual world are 2 small moons named Hi'iaka and Namaka, after daughters of the Hawaiian goddess Haumea, icy fragments thought to have been knocked loose from the dwarf planet by an ancient collision that also spun it up to its current dizzying rate. And Hi'iaka is the larger of the 2, measuring perhaps 300 kilometers across, while Namaka is smaller and orbits closer in, and together they trace paths around a primary that looks nothing like a sphere, a flattened, tumbling world spinning in the cold beyond Neptune. And this family of debris hints at violent events early in the solar system's history, collisions that shaped not just surfaces, but entire systems of moons. Spin can reshape a world. Makemake, another dwarf planet, has a small dark moon that was difficult to detect. For years, Makemake appeared to be a solitary traveler, a bright dwarf planet in the Kuiper Belt with no companion to keep it company, until the Hubble Space Telescope finally spotted a tiny moon lurking in the glare, a body so dark that it reflected only a fraction of the light of its primary and had evaded detection despite numerous searches. And this moon, informally nicknamed MK2, measures perhaps 170 kilometers across and orbits close to Makemake. Possibly once a piece of the dwarf planet itself knocked free by an impact, and the discovery reminded astronomers that absence of evidence is not evidence of absence, particularly in the dim reaches of the outer solar system, where small, dark objects can hide in plain sight for decades. And now Makemake joins the list of dwarf planets known to harbor moons, another member of a growing family. The dark can conceal companions. From the icy edges of the solar system, we turn to the strange phenomena that shape these distant worlds. Tidal heating keeps some moons warm even billions of kilometers from the sun. At the immense distances of the outer solar system, sunlight provides almost no warmth, yet certain moons remain geologically active, their interiors heated not by solar energy, but by the constant flexing of their rocky and icy shells as they orbit their massive host planets, a process called tidal heating that arises from the gravitational tug of war between a moon and its primary, and as the moon's orbit carries it closer and then farther from the planet. The changing gravitational pull stretches and compresses the interior, generating friction that converts orbital energy into heat. And this heat can be enough to melt rock, as on Io, or to maintain liquid water beneath thick ice, as on Europa and Enceladus. And without tidal heating, these worlds would be frozen solid, geologically dead and biologically barren, but instead they pulse with internal warmth that makes them among the most intriguing destinations in the search for life. Distance from the sun is not the only measure of warmth. The gravitational pull between moons and their planets creates internal friction. Imagine a ball of clay being squeezed and released again and again, each compression generating a tiny amount of heat in the material, and this is essentially what happens inside a tidally heated moon, its interior warped by the changing gravitational force as it follows an elliptical orbit around its planet, closer at one point and farther at another. And this constant reshaping causes rock and ice to rub against each other at countless microscopic boundaries, converting the kinetic energy of orbital motion into thermal energy that accumulates over millions of years. And the result can be dramatic, melting portions of the mantle, driving volcanism, or maintaining liquid oceans beneath frozen crusts. And the strength of this effect depends on the eccentricity of the orbit and the proximity to the planet, which is why moons like Io, held in a stretched orbit by the gravitational influence of neighboring moons, experience far more heating than bodies in more circular paths. Friction is a quiet engine. This tidal heating is responsible for the volcanoes on Io. Io orbits Jupiter in a gravitational tug-of-war with Europa and Ganymede, the three moons locked in a resonance that prevents Io's orbit from ever becoming perfectly circular. And this forced eccentricity means Io's interior is constantly being squeezed and stretched as it swings closer to Jupiter and then retreats, generating enough heat to melt rock and drive the most intense volcanic activity in the solar system. With hundreds of active volcanoes dotting the surface and erupting lava at temperatures exceeding 1200 degrees Celsius, and if Io orbited alone in a circular path, it would long ago have cooled to a quiet world. But the resonance with its siblings keeps the heat flowing, a perpetual engine powered by gravity and geometry. And in this way, the volcanoes of Io are not relics of an ancient past, but fresh expressions of an ongoing process. Heat manufactured in real time by the dance of moons around a giant planet. Motion creates fire. Some moons may have hydrothermal vents on their ocean floors. On Earth, hydrothermal vents are cracks in the ocean floor where superheated water saturated with minerals pours into the cold darkness, creating oases of life where bacteria thrive on chemical energy and strange creatures cluster around the warm plumes. And scientists suspect that similar vents may exist on the seafloors of moons like Europa and Enceladus, where tidal heating warms the rocky interior and drives water circulation through the rock, extracting minerals and releasing heat into the overlying ocean. And evidence for such activity has been found in the form of silica particles detected in Enceladus's plumes, grains that form only when water interacts with hot rock at high pressures, a fingerprint of hydrothermal processes occurring beneath the ice. And if these vents exist, they could provide the energy and chemistry necessary for life to arise in total darkness. Ecosystems sustained by the warmth of a flexing core rather than the light of a distant sun. Heat rising from below can nurture life above. These vents could provide energy for life forms far from sunlight. Life on Earth began in darkness, perhaps around hydrothermal vents, where chemical reactions provided the energy to build complex molecules long before photosynthesis evolved. And this precedent suggests that any moon with similarly active geology and liquid water could harbor simple organisms sustained by the same processes, organisms that would never see the sun and would not need to, drawing their energy from the minerals dissolved in hot water rising from the rocky core. And on moons like Enceladus, the ingredients have already been detected: water, organic molecules, and the chemical signatures of hydrothermal activity, a tantalizing hint that the recipe for life may be mixing even now in the darkness beneath the ice. And while no life has yet been confirmed beyond Earth, the existence of these habitable niches expands the possibilities enormously, suggesting that life may be common wherever liquid water meets rock and warmth. Sunlight is not the only fuel for existence. Cryovolcanism is the eruption of icy materials, instead of molten rock. In the cold outer reaches of the solar system, volcanoes do not spew molten rock, but instead erupt mixtures of water, ammonia, and methane that behave like lava in the frigid conditions, flowing across the surface before freezing solid, and this process is called cryovolcanism, a term that literally means cold volcanism, and evidence of such eruptions has been found on several moons, from Enceladus's geysers to the smooth plains of Ariel and the resurfaced terrain of Triton. Places where slushy material once welled up from warmer reservoirs below and spread across the landscape, and the result can be flows, domes, and fractures that mirror volcanic features on Earth, but formed at temperatures hundreds of degrees below freezing, a reminder that the same geological processes operate throughout the solar system, adapted to whatever materials are available, whether silicate rock or water ice mixed with antifreeze compounds. Volcanism wears many faces. Several moons in the outer solar system show signs of cryovolcanic activity. From the geysers of Enceladus to the smooth resurfaced plains of Ariel, from the cantaloupe terrain of Triton to the possible flows on Europa, evidence of cryovolcanism appears throughout the moons of the outer giants, suggesting that icy eruptions are a common process wherever tidal heating or residual warmth can maintain pockets of liquid beneath frozen crusts. And these features range from active plumes still erupting today to ancient landforms that record a more geologically vigorous past. And scientists study them to understand how heat is distributed within these moons and how internal reservoirs of liquid may interact with the surfaces above. And each new discovery adds to a growing picture of a dynamic outer solar system where change is not limited to the warm inner worlds, but extends far into the cold reaches where ice behaves like rock and water acts like magma. Activity does not end where warmth fades. And as we consider what lies beneath the surfaces, we discover worlds within worlds. Subsurface oceans may be common among icy moons. Once thought to be unique oddities, subsurface oceans are now suspected on a growing list of moons throughout the outer solar system, from the certain seas beneath Europa and Enceladus to the possible reservoirs under Ganymede, Callisto, Titan, and perhaps even Pluto's Charon. And this abundance suggests that liquid water may be far more common in the universe than previously imagined, hidden beneath frozen shells where tidal heating, radioactive decay, or antifreeze compounds keep temperatures above the melting point. And if life can arise in such conditions, then there could be countless habitable worlds scattered throughout the galaxy, not on sunlit surfaces, but in dark oceans beneath kilometers of ice. And the moons of our own solar system serve as natural laboratories for testing this idea, places close enough to study in detail, and perhaps one day to sample directly. And what we learn there will shape our understanding of where life might flourish beyond Earth. Oceans hide in unexpected places. The ice shells of moons like Europa can be tens of kilometers thick. Between the surface we can photograph and the ocean we suspect lies below, there is a barrier of ice that on Europa may be anywhere from a few kilometers to more than 30 kilometers thick. A frozen lid keeping the liquid water insulated from the vacuum of space above. And this shell is not static, but convects slowly over geological timescales, warmer ice rising and cooler ice sinking in a sluggish circulation that carries heat from the ocean below to the surface above. And in some places, the ice may thin enough for pockets of liquid to exist within the shell itself, transient lakes that form and freeze and form again as conditions change. And penetrating this barrier to reach the ocean will be one of the great engineering challenges of future space exploration, requiring drills or melting probes capable of descending through kilometers of frozen water while maintaining communication with the surface above. The shell protects, but also hides. Salt has been detected on the surface of Europa, hinting at the ocean below. Observations from Earth-based telescopes and the Galileo spacecraft have revealed traces of salts on Europa's icy surface, particularly in the younger, fractured regions where material from below may have been exposed. And these salts are thought to originate in the ocean itself, carried upward through cracks in the ice and deposited on the surface when the water froze or sublimated away. And the type of salt detected, including compounds like sodium chloride, suggests that Europa's ocean may be similar in salinity to Earth's seas, a briny reservoir rather than pure water, and this chemistry has implications for habitability, since salt affects the freezing point, the density of the water, and the kinds of chemical reactions that can occur. And in the yellowish stains visible on portions of Europa's surface, scientists see the signature of a hidden sea reaching up to touch the vacuum above. Surface clues point to depths below. Some moons may have underground lakes sandwiched between layers of ice. In addition to the deep global oceans detected beneath some moons, there may also be smaller pockets of liquid water trapped within the ice shell itself, lakes sandwiched between layers of frozen material where local heating or chemical conditions keep the water from freezing. And on Europa, evidence for such features comes from the chaotic terrain on the surface, jumbled blocks of ice that appear to have broken apart and refrozen in new positions, patterns consistent with lakes forming, destabilizing the ice above, and then draining or freezing as conditions change. And these shallow reservoirs would be more accessible than the deep ocean below, requiring less drilling to reach and perhaps containing samples of ocean water that have been isolated for shorter periods. And the possibility of lakes within the ice adds another layer of complexity to the interior structure of these moons, a reminder that beneath a seemingly uniform surface can lie a patchwork of hidden waters. Layers conceal layers. The pressure at the bottom of some subsurface oceans could create exotic forms of ice. Water ice can take many forms depending on pressure and temperature, and in the deep interiors of moons like Ganymede, where oceans may be sandwiched between layers of ice, the pressure at the bottom of the water column could be high enough to force the molecules into dense crystalline structures, unlike the familiar ice that forms in our freezers. Phases with names like Ice 3, Ice 5, or Ice 6 that are stable only under conditions found deep within planetary bodies, and this layered architecture, with liquid water trapped between different forms of ice, complicates the question of habitability because the exotic ice at the base may separate the ocean from the rocky interior, cutting off the supply of minerals that hydrothermal vents would otherwise deliver. Yet it also opens new avenues for chemistry and physics, processes we have only begun to explore in laboratories on Earth. Pressure reshapes even water. Scientists study Earth's ice-covered lakes as analogs for these hidden moon oceans. Beneath the ice sheets of Antarctica lie lakes that have been sealed from the atmosphere for millions of years, isolated bodies of water where microbial life persists in cold, dark conditions that may resemble those in the oceans of icy moons. And scientists drill into these lakes to study the organisms they contain, testing techniques that may one day be used to explore Europa or Enceladus. And the microbes found in these extreme environments have adapted to low energy and scarce nutrients, surviving on geochemical processes rather than sunlight, and their existence provides a proof of concept that life can endure in isolated, frozen reservoirs, a reassuring precedent for the search for life beyond Earth. And in this way, our own planet serves as a testing ground for the technologies and hypotheses that will guide missions to the outer solar system. Each Antarctic expedition a rehearsal for journeys yet to come. Earth's extremes teach us about elsewhere. From the hidden depths, we rise to the surfaces and the mysteries written in craters and ridges. Impact craters tell the story of a violent early solar system. Across nearly every moon in the solar system, impact craters record the history of bombardment that shaped these worlds. Scars left by asteroids, comets, and debris that struck with tremendous energy during the chaotic early eons when the planets were still settling into their current orbits, and the density of craters on a surface can be used to estimate its age, with heavily cratered terrain dating back billions of years, while smoother regions must have been resurfaced more recently, erasing the older wounds. And some impacts were so powerful that they sent ejecta flying across continents of ice, punched through crusts to expose underlying material, or even came close to shattering the moons entirely. And by reading this record of violence, scientists reconstruct the dynamical history of the solar system, tracing the movements of debris and the timing of cataclysms that shaped the worlds we see today. Violence writes in stone. Some moons have craters so large that they nearly broke the moon apart. On Mimas, the crater Herschel spans a third of the moon's diameter. On Tethys, the crater Odysseus covers nearly half the visible hemisphere. And on numerous other bodies, similar vast impact basins dominate the landscape, each one a testament to a collision that came perilously close to catastrophic destruction, releasing enough energy to send shockwaves through the entire moon and leave fractures on the opposite hemisphere. And had the impactors been larger or faster, these moons might have shattered into clouds of debris that would slowly coalesce into new bodies or spread into rings around their planets. And the fact that they survived tells us something about the balance between the force of impacts and the cohesion of ice and rock, a threshold that was narrowly avoided in each case. And today these giant craters remain as monuments to near misses, reminders of the violence that shaped every world in the solar system. Survival sometimes comes by slim margins. The lack of craters on some moons suggests ongoing geological renewal. When scientists examine a moon and find few impact craters, they know the surface must be young, erased, and renewed by geological processes that bury or destroy the scars of ancient collisions. And on Io, the constant volcanic activity resurfaces the entire moon within years. On Europa, the shifting ice erases features over millions of years. And on Enceladus, fresh ice, sprayed from the geysers, coats the South Polar region in pristine white. And these active worlds contrast sharply with the heavily cratered surfaces of geologically dead moons like Callisto or Mimas, where every impact remains visible indefinitely because nothing disturbs the terrain. And the difference between cratered and smooth surfaces tells the story of internal heat, of energy that keeps some moons alive, while others have long since fallen silent. And in this contrast lies a guide for understanding which worlds are most likely to harbor the conditions for habitability. Youth can be a clue to life. Strange grooves and fractures crisscross many icy moons. Across Europa, Ganymede, Dione, and a host of other icy satellites, the surfaces are etched with networks of grooves and fractures that trace complex patterns across the terrain, evidence of stresses that have cracked and reshaped the ice over geological time. And these features can arise from tidal flexing as the moon's orbit carries it closer and farther from its planet, from the expansion of freezing interiors that push against the crust, or from tectonic forces driven by convection in the ice shell. And the patterns they form can reveal the history of stress on a moon, the directions of forces acting over millions of years, and possibly the presence of liquid beneath, since fractures that open and close rhythmically suggest a shell that floats and flexes on a layer of water. And in these lines and ridges, scientists read a language of motion and change, stories of worlds that are anything but static. Cracks record forces. Some fractures open and close in rhythm with the moon's orbit. As a moon travels along an elliptical orbit, the gravitational pull from its planet strengthens when it moves closer and weakens when it retreats. And this changing force causes the moon to flex, its shape subtly deforming in a rhythm tied to the orbital period. And on icy moons with shells floating on liquid oceans, this flexing can open and close fractures in the ice, cracks that gape wide when stress is high and pinch shut when the stress relaxes. And scientists have observed this cycle on Enceladus, where the tiger stripe fractures at the South Pole are most active at certain points in the orbit when tidal forces pull the cracks apart, allowing geysers to erupt more vigorously, and these breathing fractures are direct evidence of a dynamic interior, a moon that stretches and contracts with every pass around its planet, alive in a way that static, frozen worlds are not. Cracks can breathe. The stripes on Enceladus mark the locations where geysers erupt. Near Enceladus's south pole, 4 parallel fractures known informally as the tiger stripes slice through the icy terrain, warm rifts that stand out in infrared images as bright lines against the cold background. And along these fractures the geysers erupt, jets of water vapor and ice crystals spraying into space from dozens of individual vents spaced along the cracks. And the arrangement is no coincidence, for the fractures are the pathways through which subsurface water escapes. Channels kept open by tidal stresses and warmed by the heat carried from below, and the plumes merge into a curtain of spray that rises high above the moon before falling back or drifting away into Saturn's E-ring. And if you stood near one of these vents, you would see a faint mist rising from the ground and feel the ice beneath your feet, trembling with the energy of an ocean pressing upward, a direct glimpse into the hidden sea below. The stripes are windows. Bright rays radiate outward from fresh craters on many moons. When an impactor strikes an icy or rocky surface, the force of the collision excavates material and flings it outward in all directions, and this ejecta settles in streaks that radiate from the crater like the spokes of a wheel, bright when the debris is freshly exposed and has not yet been darkened by radiation or weathering. And these ray systems can stretch for hundreds of kilometers across a moon's surface, marking young craters that have not yet had time to fade into the background. And on our own moon, the bright rays of Tycho crater are visible from Earth, while on Ganymede and Callisto similar features highlight recent impacts against darker, older terrain, and the brightness of the rays provides a rough clock for crater age, slowly dimming over millions of years as the fresh material is altered by charged particles and micrometeorite bombardment, until eventually the rays become indistinguishable from the surrounding surface. Fresh wounds shine brightest. Allow these images of distant surfaces to fade softly, like starlight dimming at dawn. Let your body grow heavier, your mind quieter. The moons continue their orbits, patient and enduring, and you are free to rest among them. Dust and ice particles constantly fall onto the surfaces of moons. Space is not empty, but filled with a thin rain of microscopic particles, fragments of comets, asteroid dust, and grains shed by other moons. And this cosmic drizzle settles onto every surface in the solar system, coating moons with a fine layer of material that accumulates over millions of years, and on bodies with no atmosphere or geological activity to remove it, this layer can grow centimeters thick. A blanket of tiny impacts that softens the underlying terrain and alters its reflectivity. And some moons are darker because they have swept up more carbonaceous dust, while others remain bright, where fresh ice is deposited faster than it can be buried. And this gentle bombardment connects distant objects, carrying material from one part of the solar system to another, mixing the signatures of many origins into a single surface. And in this slow rain, there is a kind of sharing, a redistribution of matter that links all the worlds of our cosmic neighborhood. Even emptiness delivers something. Some moons share their orbits with rings of debris. At certain distances from Saturn, moons do not orbit alone, but share their paths with trailing or leading swarms of smaller bodies, particles and fragments locked into gravitationally stable points that move ahead of or behind the moon in its orbit. And these co-orbital companions can range from dust-sized grains to chunks several kilometers across, remnants of collisions or captured debris accumulated over billions of years. And the slight gravitational influences of the moons themselves help to shape and maintain these clusters, herding particles into specific zones the way a shepherd keeps a flock from straying. And some moons actually swap orbits periodically, two small bodies dancing around a shared track, trading places every few years in a gravitational do-si-do that is unique in the solar system. And in these complex arrangements, we see the delicate balance of forces that governs the motion of small bodies near giant planets. Company can be orbital. Shepherd moons help shape the edges of planetary rings. Saturn's rings are not uniform sheets, but intricate structures of gaps and ringlets, and some of this complexity arises from the gravitational influence of small moons orbiting near or within the rings themselves, bodies whose gravity nudges ring particles inward or outward, sweeping clear gaps and sharpening edges that would otherwise blur over time. And these shepherd moons act like cosmic border collies, keeping the particles in line and preventing them from spreading into undefined clouds. And examples include Prometheus and Pandora, two small moons that bracket Saturn's F-ring and maintain its narrow, braided structure, and Pan, a tiny moon that orbits within the Encke gap and keeps that division swept clean. And without these shepherds, the rings would slowly diffuse and lose their crisp definition, fading into the background of space. And so the beauty we see owes much to the patient work of moons too small to see with the naked eye. Small bodies can do large work. Tiny moonlets embedded in Saturn's rings carve gaps as they orbit. Within the dense bands of Saturn's rings hide countless tiny moonlets, bodies only a few hundred meters across, embedded in the swarm of icy particles and revealed by the narrow wakes they leave behind, propeller-shaped disturbances where gravity clears a path through the surrounding material before the ring closes back in. And these moonlets are too small to sweep clear permanent gaps like the larger moons do, but they create temporary clearings that drift along with them as they orbit. Thousands of miniature shepherds plowing through a sea of ice, and the Cassini spacecraft detected hundreds of these propeller features during its years at Saturn, each one a fingerprint of an unseen moonlet creating order in the midst of chaos. And in these tiny disturbances, scientists see the seeds of future moons, fragments that may one day grow by accumulating more material or merge with neighbors to build larger bodies. The smallest can still leave a mark. Some moons may eventually be destroyed and become new rings themselves. The fate of moons that spiral too close to their planets is not always to crash into the atmosphere or surface, but sometimes to be torn apart by tidal forces before they reach that point, shredded into fragments that spread out along the orbit and disperse into a ring of debris. And this process may already be underway around some planets, with moons like Phobos and Triton destined to cross the Roche limit in the distant future. And when they do, they will not simply vanish, but transform. Their substance redistributed into glittering arcs of ice and rock that could persist for millions of years before slowly raining down onto their host worlds. And in this way, rings and moons are not separate phenomena, but stages in a cycle, moons forming from rings and rings forming from moons, a continual exchange of material governed by gravity and time. Destruction can be a form of renewal. And as we near the end of our journey, we look to the future and what awaits these mysterious worlds. Future missions aim to explore Europa's ocean for signs of life. In the coming years, spacecraft from Earth will venture to the Jovian system with instruments designed to probe Europa's icy shell and sample the material that may be escaping from the ocean below. And among these is the Europa Clipper, a mission that will fly past the moon dozens of times, mapping the surface in detail and searching for plumes of water vapor that could be captured and analyzed, and further in the future. Landers and even submersible probes may be developed to penetrate the ice and explore the ocean directly, a journey that would take us into a realm no human technology has yet touched. A dark sea beneath kilometers of frozen water where the answers to some of our deepest questions may be waiting, and the engineering challenges are immense, the risks significant, But the potential reward is nothing less than the discovery of life beyond Earth. We are building the tools to ask the question. A spacecraft called Dragonfly will one day fly across the surface of Titan. Unlike any previous mission, Dragonfly is a rotorcraft lander designed to take advantage of Titan's thick atmosphere and low gravity, conditions that make powered flight easier than on any other world in the solar system. And when it arrives in the mid-2030s, it will hop from site to site across the Moon's surface, covering distances that would be impossible for a wheeled rover, sampling the organic-rich terrain, analyzing the chemistry of dunes and craters, and searching for prebiotic molecules that could shed light on how life begins. And over the course of its mission, Dragonfly will travel hundreds of kilometers, exploring a landscape of methane lakes, ice mountains, and chemical plains, sending back images of a world that has so far been glimpsed only through the haze. And in its buzzing flight lies a new chapter of exploration, one that brings the tools of helicopter aviation to a moon nearly 10 times farther from the sun than Earth. Flight expands the horizon. Sample return missions may one day bring back material from Enceladus. Enceladus offers a unique opportunity in the search for life, because its geysers spray samples of the subsurface ocean directly into space, eliminating the need to drill through kilometers of ice. And scientists have proposed missions that would fly through these plumes, capture particles in aerogel or other collection media, and return them to Earth for detailed analysis in laboratories far more capable than any instrument that could be sent to Saturn. And such a sample return would allow researchers to examine the organic molecules, salts, and potential biosignatures under every tool available, looking for patterns that could only arise from biological processes. And while the journey would take many years in each direction, the scientific payoff could be immense, perhaps the first definitive evidence that life exists beyond Earth, delivered on a spacecraft carrying a few grams of ice from a moon more than 1 billion kilometers away. Samples speak louder than signals. Colonizing moons like Titan or Ganymede may one day be possible. As humanity looks beyond Earth for places to settle, some moons stand out as potential destinations, and Titan in particular offers advantages that no other world can match. A thick atmosphere that provides radiation shielding and allows for winged flight, abundant hydrocarbons that could serve as fuel and raw materials, and a surface where pressures are comfortable even if temperatures are not. And while the cold would require insulated habitats and the chemistry would demand careful engineering, the resources are there for those willing to adapt, and Ganymede, with its magnetic field and possible ocean, presents its own possibilities, as does Callisto with its stable, radiation-shielded environment. And these visions remain distant. The challenge is immense, but the moons of the outer solar system are not barren wastelands devoid of promise, and future generations may look back on our era as the time when humanity first began to dream seriously of living among them. Possibility stretches outward. The moons of our solar system may hold the key to understanding how life begins. If life is found on Europa, Enceladus, or Titan, it will either share a common ancestry with life on Earth, suggesting that biological material was exchanged between worlds in meteorites and comets, or it will have arisen independently, proving that life is not a one-time accident, but a natural outcome of certain chemical conditions. And either way, the discovery would transform our understanding of biology and our place in the universe. And even if these moons turn out to be sterile, studying their chemistry will reveal how close non-living systems can come to crossing the threshold into life, illuminating the steps that must have occurred on Earth before the first cell divided. And so the exploration of these worlds is not merely an exercise in planetary science, but a quest to answer one of the most profound questions humans have ever asked. And the moons stand ready to offer whatever answers they hold. Life's story may be written in many places. Each new discovery reminds us how much remains unknown. Every time a spacecraft flies past a moon and returns images, every time a telescope detects a new satellite or a spectrometer identifies an unexpected compound, the boundaries of our knowledge shift, and the map of what we do not know grows larger rather than smaller. For each answer opens new questions, and each feature explained reveals others that remain mysterious, and the moons of our solar system have surprised us again and again. From volcanoes on Io to oceans on Enceladus to the cantaloupe terrain of Triton, phenomena that no one predicted until the evidence arrived. And this pattern suggests that the future holds wonders we cannot yet imagine, that the moons we have barely glimpsed, the small irregular satellites and the distant companions of dwarf planets, may contain stories as rich as any we have already heard. And in this expanding frontier of ignorance, there is not despair but invitation, a call to keep looking. Mystery is not emptiness. The moons orbit on, indifferent to our gaze, holding their secrets close. Whether we observe them or not, the moons continue their patient circuits around the planets, Io erupting, Europa flexing, Titan's rivers flowing, Enceladus spraying into the void, all of it happening in the darkness, whether or not any human eye is watching. And this indifference is a kind of reassurance, a reminder that the universe does not depend on our attention to proceed. That the processes shaping these worlds have been underway for billions of years and will continue for billions more regardless of what we do. And yet we are here, awake and curious, reaching out with telescopes and spacecraft to touch the edges of these distant mysteries. And in that reaching there is something profound, a small species on a small planet striving to understand companions it will likely never visit in person, drawn by nothing more than the desire to know. The gaze is ours, the patience is theirs. And yet, in their silence, they invite us to wonder. The moons do not speak, they do not beckon with voices or signals, and yet there is something in their presence that draws the mind outward, a silent invitation written in ice and rock, and the patterns of light falling across distant surfaces. And perhaps it is simply that they exist at all, worlds we did not make and do not control, places where the familiar rules of physics play out in unfamiliar settings, where water freezes into shapes we have never seen and fire erupts without air. And in contemplating them, we are reminded of our own smallness and our own capacity for wonder, two truths that sit comfortably together in the quiet of a night spent looking up at the sky. And this invitation is open to anyone who cares to accept it. No credentials required, no journey necessary beyond the one that happens inside your own mind, as you imagine what it might be like to stand on a frozen plain beneath the glow of a distant giant. Wonder is its own reward. And so our journey through the mysterious moons of the solar system draws gently to a close. We have wandered from our own familiar moon, drifting past the small, cratered companions of Mars, through the volcanic fury of Io and the frozen promise of Europa. We have walked the hazy shores of Titan, felt the icy spray of Enceladus, and gazed upon the strange, tumbling forms that orbit in the cold beyond Neptune. From hidden oceans to shattered surfaces, from geysers of ice to mountains of ancient stone, these moons have whispered their secrets into the quiet of the night. If these journeys bring you peace, consider leaving a like or subscribing so that more weary minds might find their way here. There are more wonders waiting, and we would love to have you return whenever rest calls. Right now, as you listen, these moons continue their silent paths around their planets. The geysers of Enceladus still erupt into the void, the tides beneath Europa still rise and fall, and somewhere in the darkness beyond Pluto, Charon keeps its eternal watch. These processes have continued for billions of years, and they will continue long after tonight is over. Let your eyes grow heavy if they have not already, and allow them to close. Take a slow breath, deeper than before, and feel it release any remaining tension from your shoulders and your chest. Let your hands rest open, your jaw soften, and imagine yourself drifting through the calm silence between the moons, weightless and at peace. Tonight, as you rest, the moons continue their quiet orbits. Io glows with hidden fire, Europa's ice creaks above its sleeping ocean, and Titan's methane rivers flow beneath an orange sky. Triton spirals slowly inward, and far beyond, Charon and Pluto turn together in the cold. You are a small, warm presence within this vast cosmic dance, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that beyond the familiar sky, 100 moons are circling still, each one a world waiting to be known. This has been Drowsy Discovery. Good night.